What's going on, guys? This is Drew, and I am the SDSU EE tutor. Let's do this. So let's take a second to absorb the information on this screen. The problem says, let's find the transfer function VO over VS. It wants the bandwidth, the band center, and the quality factor. Okay, the bandwidth, this is B. That's the variable we have been focusing on. And that's all I'm going to say about this, because we'll talk about that later. This is omega naught, the resonant frequency. This is the quality factor. This guy equals omega O over B. And we'll go over this in a little bit. But let's take a look at this first. Op amps. So the golden rules for op amps: VA equals VB. Okay, so this voltage A, the red, equals the voltage at the B, always. Second rule of op amps: no current enters or exits the op amp terminals. So that means that the current going through this resistor, I, right, this equals 0. Okay, because we said no current enters or exits this terminal. The only thing connected to this is this one wire, this one branch. And we said that that current equals 0. So if V equals IR, right, and I equals 0, that means V equals 0. Okay, so that means that this thing is essentially just a shorted wire. Okay, which means that B is 0 volts. So that is very important. B equals 0 volts. Right? And because we said VA equals VB, we know that this equals VA. So now we need to figure out how to get an equation out of this guy so that we can get VO over VS. So we're going to use Kirchhoff's current law at node A. We'll say the current going in has to equal the current going out. Okay, so the current going in is going to be VS minus VA divided by 1 plus 1 over S. Okay, and this is going to equal VA minus VO over 2 plus VA minus VO over 2 over S. So if you look at how I got these two guys, this just came from splitting up the currents going through the resistor and the capacitor up on the top branch. So everybody agrees that V equals IR, correct? So if we take this voltage and subtract this voltage, that would give us a V, right? And then if we just divide it by each individual resistance or impedance, then that will give us our current I. So V over R for each certain case. So we do it for this guy is right there, and then going through the capacitor is up top, and that's the second term. Okay, moving forward. So let's try and simplify this thing a little bit, because this looks like it needs some algebra. So first of all, we said VA equals 0. So we can just get rid of those terms. So this term, the S will jump up to the top. So this will be negative VO times S over 2 plus negative VO over 2. This equals VS divided by So let's multiply this whole thing times S over S, because this will make our lives much easier in the future. And pay attention to this, because this is a common trick to simplify things. So now we'll have an S on top, but that will be divided by S times 1 is S, plus S times 1 over S is just 1. So we don't have to deal with this 1 over S down in the denominator. We have whole numbers. And we don't need this line. Okay, so now let's multiply everything times 2. 2. So this will be 2S over S plus 1 times Vs, and this shall equal negative VO minus VO times S. And obviously we can pull out a VO from here, so this will become negative VO times 1 plus S. Okay, so 2S over S plus 1 Vs equals negative VO 1 plus S. So we want VO over Vs. So let's divide both sides by Vs. Those will cancel out. Vs. And then we want to divide both sides by 1 plus S. 1 over 1 plus S. And let's factor this guy out, so this will be S plus 1 plus S squared plus S, or S squared plus 2S plus 1. And our final answer is VO over Vs equals negative 2S over S squared plus 2S plus 1. Huzzah! Okay, so now we got the answer, and the second part of the problem was it wanted the bandwidth, the band center, or the resonant frequency, and the quality factor. So the bandwidth, B, the bandwidth is always going to equal the constant in front of S. Okay, when you have a polynomial down here, your bandwidth is going to be this number. So the bandwidth equals 2. Okay, omega naught. So from this equation, this term right here, this is said to be omega naught squared. Okay, and this thing equals 1. So if we take the square root, that will cancel out and we'll just be left with omega equals the square root of 1, which equals 1. So this equals 1. And the quality factor is just a ratio of the resonant frequency to the bandwidth. and this equals 1 over 2. This portion is not very difficult. This is free points. Obviously, these things are a little bit more complex than just pulling numbers off of the transfer function and understanding what they mean and what they do. But for our sake, we're trying to pass the exam right now. So we're going to leave it at that, and if I have time, yeah, we're going to leave it at that. Let's go to problem 2. Okay, so for problem 2, we want VO over VS. And we are looking for the transfer function H, but we want it in terms of omega. Okay, last time we did it in terms of S. We don't want that. We want it in terms of omega. And then it's asking us to plot the Bode plot for HDB. So let's inspect our circuit over here. And the first thing that I notice is this resistor hooked up to this terminal. Rule number 2 says that no current flows into or out of the op amp. So this I equals 0. I equals 0. So this voltage equals 0, and that means that this is a short circuit. So this terminal is directly connected to VO. This is VO. And because this terminal is VO, that means that this terminal is also VO. Alright, now we can try and set up an equation. And once again, we're going to use Kirchhoff's current laws. Current going in must equal the currents going out. I've got Vs minus Va over 1 is going to equal VA minus VO divided by 2 times S. Alright, all I did was bring the S to the top. Plus VA minus VO over 1. And this is pretty simplified, which is pretty sweet. So, but let's try and collect terms. So this is VS minus VA. This equals S over 2 VA minus S over 2 VO plus VA minus VO. So we can move VA over to this side. So it'll be VS will equal VA times S over 2 plus 2. Alright, because if we move this over, we have a VA already over here. That'll be VA plus VA gives us 2 VA. So that takes care of that, and then minus VO s over 2 plus 1. So let's multiply everything times 2. 2 Vs equals Va times, if we multiply 2 times this term, we get S plus 2 times 2 is 4 minus VO. 2 times this term is S plus 2. Okay, so this looks pretty much simplified, and let's leave this here. See what else we can get from our circuit. So another relation that we can find from this circuit is that the current flowing from VA to VO, this current going through this resistor, is the same as the current going through this capacitor. So how does that help us? You're going to see right now we have VA minus VO divided by 1. That has to equal VO over 1 divided by S, but because the S is on the bottom, I'm just going to move it up to the top right there. So now we have another relation, and this is what we're going to use to get the answer. I'm going to move VO to the other side. This will become VA equals VO plus VO times S. We can take out VO. This will be S plus 1. This will equal VA. So now we can take this term and substitute it in for VA right there. So we have 2VS equals VO times S plus 1 times S plus 4 minus VO S plus 2. Okay, so let's FOIL these out. This will be VO times S squared. S times 4 is 4S, plus 1 is 5S, plus 5S, and then plus 1 times 4 is 4, so plus 4, and then minus VO times S plus 2. So this term will become VO times S squared. 5S minus S is going to be 4S, so plus 4S. And 4 minus 2 is going to leave us 2, so plus 2. And this will equal 2VS. Go down a little bit more. We want VO over VS, so I'll divide both sides by VS. These get crossed out, and then we want to get this term on the other side, so we'll divide both sides by S squared plus 4S plus 2. That goes away, goes over here. And this is our answer. So VO over VS will equal 2 divided by S squared plus 4S plus 2. So this equals H of S. Right, but we said we want H of omega. Well, if we remember, S just equals J omega. So let's plug in J omega everywhere we see an S. So this will be 2 over j omega squared plus 4 times j omega plus 2. Alright, and we know that j squared is just -1, so let's change that as well. So this will equal 2 over negative omega squared, right, because there's a -1 in front of it, because j squared equals 1, plus 2 plus 4j omega. Okay, so I grouped the omega in the 2 over here because these are the real terms, and then this is the complex term. So I just wanted to separate them because it'll make our lives simpler. Okay, so this is our answer. This thing equals, oops, h of omega. Now, for the unfortunate souls who do not have TI-89, we actually have to plot the Bode plot. If you have a TI-89, you can just plot this based off your transfer function, and you're good to go. But everyone else, we need to calculate this. So we need to calculate we want to calculate 20 log of the magnitude of h of omega. Okay, this magnitude thing is very important because we have a complex term down here, so we're going to need to do the whole a squared plus b squared thing where you get the magnitude. Basically, we just want to evaluate this for multiple terms of omega and then plot it, and that's it. So the magnitude of h of omega is going to be equal to 2 over the square root of negative omega squared plus 2, this term squared, plus 16 omega squared. Notice that we disregard this j when you're finding the magnitude. Okay? For example, if you had 5 minus 4i, the magnitude wouldn't be 5 squared minus 4 squared. You want the positive values because you want the magnitude, you want the largest value. So basically all we have to do is plot this function for different values of omega, and on the graph we're going to plot -3, -1, 0, and 1. So for a logarithmic graph, this corresponds to 10 to the -3, 10 to the -1, 10 to the 0, and 10 to the 1. So if you punch this in your calculator, the first term you're going to get something very close to 0. The second term you're going to get something very close to 0. On this guy you will get -6.28, and for this term you get -34.5. So all we have to do is plot this on our graph and make a handy dandy little curve. So we say this is 0, this is 0. We said this was negative 6 point something, and at 1 we were at negative 34. Cool. And that's it. So that's all I got for you guys. Thanks for watching, and check out the group session.